Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're continuing with our series on writing a ray tracer in C++ using as far as possible only the standard libraries and the SDL2 library so that we can display results in a window. This particular episode is going to focus on continuing with our little mini-series looking at procedural textures and in particular procedural noise. So in the last episode we looked at how we can implement value noise, which is a very simple type of procedural noise, and in this episode today what I want to do is to extend on that to look at how we can implement gradient noise, which is based on very similar principles but makes it a little bit more sophisticated so that we can create slightly more interesting patterns. We're also going to go on to look at how we can use the noise to perturb a sine function, which is the basis of making nice looking textures like marble or clouds and things like that. So hopefully that will be of interest. Before we dive into that though, I just want to say quickly, as I always do, that if you like this video, please do remember to hit that like button. It really does make a difference with the YouTube algorithm. And if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future content. Thank you very much. Right, without much further ado, let's jump into it and let's have a look at gradient noise. Okay, so this is now episode 16 of our series on writing a ray tracer in C++. And we're going to be looking at gradient noise. Okay, so I wanted to just start with some examples of the kind of patterns that we can make with gradient noise, and basically we're talking about things like this. So as we saw with the marble example, the marble cube that I showed in the previous episode, we have the basic characteristics of procedural noise in that over a very small scale our colour of our texture varies only a little bit, but over a larger scale it varies quite a lot. And gradient noise can be used to create more sophisticated patterns than we could do with value noise. So we could go on to create things like this. I mean, this obviously reasonably resembles marble, I mean not exactly, and that this is the sort of thing that we're going to talk about being able to create. And you can see how this starts to allow us to make some more natural looking materials and textures, which obviously can be very useful. Okay, so in the previous episode where we looked at value noise, if you haven't seen that, I strongly suggest you go back and have a look at that now, because I'm not going to go over the basics, but we talked about how we divide our texture into squares or cells or whatever you want to call them, and we identify the four corners around the point at which we want to evaluate the color of our texture. And then for value noise, we simply had a value stored at each of those corners, and we simply use bilinear interpolation to compute the value at our point of interest, shown here in blue. So in this hypothetical scenario, we have a box defined by four corners labelled A, B, C and D, and we have the point of interest, the point within the texture where we want to evaluate the colour, shown here in blue. And with gradient noise, instead of defining a single value at each of the corners, we actually now define a vector. And this could of course be random or not, that just depends on how you want to do it. As in the previous episode, I'm not going to talk about hashing algorithms or the use of pseudo-random sequences to avoid having to store everything. As I explained before, for what I'm doing, it's perfectly acceptable to store a vector at every corner, or in the case of value noise, a value. But for gradient noise, it's a vector. So what we do, we simply define a possibly random vector at each corner, and then we compute a vector from each corner to the point of interest. Okay, so the vector from corner A to our point is the vector PA, from corner B to our point is the vector PB, from corner C to our point the vector PC, and from corner D to our point the vector PD. And we have our four vectors at each of the corners, which are VA, VB, VC and VD respectively. And then what we do is simply to compute the vector dot product for each pair of vectors for each corner. So for corner A, we compute the dot product between the vector VA and the vector PA, and that gives us a scalar quantity dA. And we do the same thing at corner B, where we compute the dot product between the vector VB and the vector PB, like so, and that will give us another scalar quantity. And we repeat that for all four corners, and that then gives us four scalar quantities, or simply four values, dA, dB, dC, and dd, sorry. And then we simply use the bilinear interpolation as we talked about in the previous episode. That is actually it. It really is that simple. It's nothing complicated. We are simply Whereas for the value noise, we stored a value at each corner and we simply use bilinear interpolation. In this case, we store a vector at each corner and we compute the vectors from the corner to the point of interest, and we compute the dot product of those vectors, and that gives us the scalar quantity. And once we've got the four scalar quantities, we simply use bilinear interpolation exactly as we did before. And actually that's it. It's really that simple, but the effect that that has in terms of the patterns that we can create is quite remarkable. Okay, so as in the situation we had before, we could define our texture to contain more than one square. So in this case, we have a 2x2 grid of squares, and we have a point of interest in some square here, and of course then we identify the four corners of the square that that point is in. We obtain the vectors at each of those corners, A, B, C, and D. We compute the vectors from each corner to our point, and then we go on and we compute the dot products and the use bilinear interpolation as I've just talked about. So all of that is exactly the same as what we've seen before. So I mentioned in the previous episode about the difference between using linear interpolation and using smooth step interpolation. And that really, once we start talking about gradient noise, the difference that that can make becomes a lot more obvious. So if we look at this example here, so this is a very simple texture that's been created using linear interpolation, and you can see the problem with the sharp corners that we get between the different squares. And in fact, you can literally see where the squares would be. So you could see clearly this was a 3x3 grid of squares because we get these sharp angles. Now, if we do exactly the same pattern, but use smooth step interpolation, we get something much different. You see now this is much smoother, much more organic looking, and we can no longer see clearly where the boundaries of the squares would be. So let's just have a look at that again. That was linear interpolation and smooth step interpolation. Linear, smooth step. Okay, it really does make a big difference. I'm trying to keep this episode short, not going into too much of the details that I mentioned before. So if you don't know what smooth step interpolation is, go back, have a look at the previous episode where I explain it there. Okay, so that's really everything for the theory of gradient noise. It's really very simple. I just want to show some animations that just illustrate it a bit more clearly. So in this case, we have a single square of gradient noise, and we are simply rotating the vector at each corner so that you can see clearly the impact that rotating the vectors has. Now, this is different to the value noise example where we simply had a value and we just had to change, its magnitude. In this case, we're keeping the magnitude of the vector as 1 in all cases, but we're simply rotating them. And you can see the impact that that has quite clearly on the pattern. Of course, in reality, we would use random vectors, so this is the same example, but now we're going to move the vectors at the corners to some random positions, and you can see quite clearly the kind of patterns that we're able to generate. Of course, we can increase the number of squares in our grid. So in this case, we have a 2x2 grid, again with random vectors, and you can see, again, the kind of patterns that we're able to create. Same example with a 3x3 grid. As with the value noise, we simply increasing the size of the grid means we can capture more and more detail. Now, this is just an interesting example because in order to create really interesting patterns, what we want to do is use the noise to perturb another function. So everything that I've shown so far has been based on simply plotting the value of the noise itself, or using the value of the noise itself to feed into a color map and then to decide the color of the texture at that point. That is not the best way of using procedural noise. The best way of using procedural noise to create nice, organic, natural-looking textures is to use the noise to perturb another function. So what we're going to do is we're going to use a simple sine function of u and v, okay, in our texture space, and then we're going to perturb that with the noise, and we're going to have a look at exactly what kind of patterns that can create. So let's have a look. So in this first example, in part 1, we simply have a sine wave, and we are increasing the frequency of our sine wave, or decreasing the period from 0 up to 4 pi. As you can see there, as we increase the frequency, obviously we get more and more waves of our sine across our texture. And this is a sine of u plus v, so it appears diagonal across our uv space. Okay, well that's exactly what we'd expect. So let's add a noise function to that. So in this example, we've got the sine wave from before, and we are adding to that a noise function, okay, so which is a gradient noise function similar to what we've just been talking about. As we scale the amplitude of that noise function up from 0 up to 4, you can see that the noise is perturbing the sine function. So you see where we've put the noise term, it's not altering the magnitude of the sine, it is altering the phase. Okay, so you see how the noise is perturbing the sine function to create the pattern. And in order to create really interesting patterns, what we can do is we can layer multiple noise functions together. So in this final example, we have the sine, as before, plus the noise function that we've just looked at, plus now another noise function, which we are now going to run from 0 to 4 amplitude, exactly as before. Okay, so the second noise function can have a different number of squares, it can have a different size and different level of detail, and the idea is that you build up multiple noise functions that add correspondingly smaller levels of detail, and you can add as many as you need in order to get the level of detail that you want. I think in sort of professional kind of circles where they're doing things, it would not be uncommon to have tens or maybe even hundreds of noise functions layered together to really create the level of detail that you want. Of course, for what I want to do, I don't need anything that sophisticated, but it's the basic principles of how it all works. Okay, so that's really everything for the theory and looking at what gradient noise actually does. Let's jump into the C++ code and let's have a look at how we can implement it and actually make it happen. Okay, so as always, starting at my terminal window, we have here, this is the root folder of the QB Raytrace project. If you've cloned it from the GitHub repository, this is what you'll have, or if you've been following along, you should have something similar. If we go into the QB Raytrace directory or folder and go into the QB noise directory that we created in the last episode, we have noise base and val noise generator that we created before, and what we've added today, or what we're going to add today, is gradient noise generator or GRD noise generator .hpp and .cpp. Okay, and we've also created some textures to actually make those work, and we've modified the scene file so we can see what's going on, but we'll have a look at all of that. Let's just go back to the root folder of the project. Now let's have a look at the actual noise generator class. Right, okay, so this is gradient noise generator.hpp. Okay, so this is very similar to the value noise code. There's not that much different. As before, we put this into our QBRT namespace and into the noise sub namespace. And we create the class is gradient noise generator, or GRD noise generator, which inherits from the noise base public class, which we include here, of course. We have our constructors and destructors. This class is intended to be is overriding noise base, so we declare that is declared as virtual and is overridden with a destructor, and we have the virtual get value function as well, which returns the value at a particular coordinate in the texture space, and as before we have the function to set up the grid. We now have a private function here, which is compute norm disp, which I will explain later. And we also now, we now have to store a grid of vectors rather than simply a grid of values. So before we used a std vector of std vectors of doubles to store the values, and what we do now is we simply have two of those. So we store the x value and the y value of the vector at each corner. And as before, we have our wrap flag m_wrap that I talked about in the previous episode. That is it for the header file. It's really not very much code there. So let's go and have a look at gradient noise generator.cpp. There we go. Okay, so this is the CPP file. Obviously, we hash include the header file that we've just talked about. In our constructor, we simply configure the default grid by calling setup grid with the size of 2. We have a destructor function which doesn't need any code, and I'm going to talk about setup grid first. So let's just go down to that. So here we are. This is the setup grid function. Now this is very similar to the code that we had for the value noise. It accepts an integer input describing the scale, which we store in m_scale. As before, we set up a random device and set up a seed sequence, and we can either use the seed sequence or not, depending on what we want to do. As I've explained here in the comments, if we use the seeded version, we'll get a different pattern every time. Or if we use a fixed seed or without the seed, then we'll get the same pattern every time. And it just depends what you want. If you want it to be predictable, if you're doing animations and things, you don't want it to change every frame. Okay, so do bear that in mind. We create a uniform real distribution called random dist between 0 and 1. And now we're going to create a grid of random vectors, okay? And the scale variable here defines how many grid squares that we want. So a scale of 1 means a single square, 2, 2 by 2, 3, 3 by 3, and so on. So we clear our two variables that we're using to store the x and y coordinates of the vectors, and then we resize them to m_scale plus 1, of course, because a 2 by 2 grid has a 3 by 3 grid of corners, if you think about it, and so on, okay? And we initialize all the initial values there to 0. I've talked about that before for resizing and dealing with two-dimensional arrays, so I won't go over that again now. We then loop through all of our corners. For each corner, we create a random angle, a random theta. Now, this is important. You might think that you could actually just create a random value for x and a random value for y. And if you're not convinced as to why that doesn't work, I actually suggest you try it, have a go, modify the code to do that, and you'll see that instead of getting nice circles, what you end up with is a square shape. And that will show in the texture. Okay, so it is much better to do it the way that I've done it here, where we create a random angle, theta, by calling our random distribution, multiplied by 2 and multiplied by pi. So that gives us our angle there in radians. So the random distribution gives a value between 0 and 1, so we now get a value between 0 and 2 pi. And then we're going to convert that to Cartesian coordinates, assuming that the radius, or r, is equal to 1, okay, which is what we want. We want the magnitude of the vector to be 1 in every case. So we compute a double v_x is simply equal cos theta, and vy is equal to sine theta, okay? Really simple. And then we simply store those. So m_vector grid x dot at y is equal to vx, and m_vector grid y dot at x dot at y is equal to vy. And that's it. Really very simple. Quite a simple extension of the code that we looked at in the last episode. And as before, if we deal with our m_wrap variable, if we want to do wrapping, we just make sure that the values at the edges match up, left and right, and up and down, or match across u and across v would be a better way to describe it. Okay, we also have the compute norm disp function that I mentioned. Now this accepts 4 inputs and 4 doubles, x1, y1, x2, and y2. And what this does is simply compute the difference between the two vectors, so vector 1 and vector 2. So we have xcomp is x1 minus x2 and ycomp is y1 minus y2, and it simply returns a std vector of type double xcomp with containing xcomp and ycomp. Really very simple, just makes the code a bit tidier. So let's go back, let's have a look at how we actually compute the value. Okay, so this is the function that really does all the work. It accepts as input 2 doubles, x and y, which describe their position in the UV space. I could have called them u and v, I'm not sure why I went with x and y, but never mind. As in the case of the value noise, we first ensure that they're cyclic by using the floating point modulo operator, and then we convert them to a range of 0 to 1. As these come into here in our UV coordinate system that I'm using, they will be between -1 and 1, so we add 1 and divide by 2 to make them between 0 and 1. We compute our grid spacing is simply 1 over the scale, remembering to static cast the scale to double first, because it's an integer. We then compute the local x and y, so that's our position in the local grid, again just using the floating point modulo operator with x and grid spacing. And we've just computed, and we do the same for y. And we compute the grid corner indices, so this is exactly the same as the code we talked about in the previous episode, so I won't talk about it again. Just computes the indices into our arrays. Okay, so we compute corner 1 x index and corner 1 y index, corner 2 x index, corner 2 y index, and so on. So those are the indices into our arrays. We then extract the 4 vectors, so we're extracting these as type std vector double. v1, which we then from there we extract m_vector grid x dot at c1xi dot at c1yi and m vector grid y at c1xi dot at c1yi. Okay, so I think you can see what's going on there. We're extracting the two values, the one value from m_vector grid x and the other value from m_vector grid y, each one at the indices given by c1xi and c1yi. Okay, and then we do that for the other 3 corners, v2. So now we have 4 vectors, v1, v2, v3, and v4. We then want to compute the locations of the corners. Okay, so we compute c1x. The location of that corner is at c1xi, okay, which we static cast a double because it's the integer, and we simply multiply by the grid spacing. Okay, And then we're going to compute the displacement vectors. Okay, so these are the vectors from the corners to our point of interest, which are going to be d1, d2, d3, and d4. And we use the compute norm disp function that I've just talked about. We pass to it x, y, and c1x, c1y, and c2x, c2y, and so on to give d1, d2, d3, and d4. And then we simply compute the dot products, and I haven't done that using any kind of linear algebra library because for two-dimensional vectors it's incredibly simple. dp1, for example, is simply equal to v1 dot at 0 multiplied by d1 dot at 0 plus v1 at 1 times d1 dot at 1, and that's it. And we do that for the four corners, so that gives us four scalar values, dp1, dp2, dp3, and dp4, and then we simply use bilinear interpolation exactly as before. We compute our x weight as local x times the scale, and y weight as local y times the scale, and then we use the lerp function, which comes from the noise base class, and we talked about in the previous episode to give t1 and t2, and then we interpolate between t1 and t2 using x weight, and that is our final value. Okay, that is actually it. That is everything that we need to do to implement gradient noise. Okay, so let's have a look at how we can create a very basic texture class that will implement gradient noise using this class. Okay, so this is basic-noise.hpp, which is a very simple class designed to just really demonstrate. So everything pretty much as before. We bring in gradient noise generator and value noise generator. I'm not actually using value noise generator, never mind, we've included it anyway. This is in the QBRT namespace and the texture sub namespace. It's class basic noise that inherits from texture base. Okay, so I've talked quite extensively about my texture classes before, so I'm not going to go over all of that at the moment. Suffice to say that we store, we've got all the standard functions. What have we got? Yes, so get color. These ones we override from the texture base, and then we've got set color map, set amplitude, and set scale, the same as we had for value noise. Set color map simply allows you to obviously set the color map. Amplitude is for the amplitude of the noise, and scale is the scale of the grid that we want. So we store a color map. It's of type color map from the texture namespace, m_color map. We have a flag to say whether we have a color map or not. We store a noise generator instance. This time, of course, we're using the GRD noise generator that we just talked about. We store an amplitude, a default value of 8, and we store a scale with a default value of 3. Okay, that is the HPP file. Let's look at basicnoise.cpp. Okay, basicnoise.cpp, we bring in the header file that we've just talked about. We have in our constructor, we set this up with the default scale using setup grid to configure the noise generator. And then get color method. This is all the standard code for how I deal with textures for my texture classes. So we get our UV coords to get our input location, we apply the transform, the local transform that can be applied to the texture, and we extract from that new U and new V, okay, both as doubles. Okay, we create a QB vector type double for local color. It's 4-dimensional, RGB alpha. If we don't have a color map, we simply set it to purple, okay, to indicate that something is wrong. It should be obvious in the scene. If we do have a color map, then we actually generate, I call this generate the base function. What we're actually doing is interrogating the noise generator to get that value. So we get a value called map position, which we get from noise generator, the noise generator instance, by calling the get value function. We pass new U and new V. We multiply that by the amplitude, and then I'm just using std clamp to make sure that that value is always between 0 and 1. Okay, and then we use that map position. We pass it to the getColor function from the color map class, and that will, color map instance, sorry, and that gives us our local color, which is what we then return. And it's really that simple. So to set up the color map, we have the setColorMap function, simply stores a color map and sets the flag to true to show we have one. SetAmplitude simply stores the amplitude, and setScale simply stores the scale and calls the setUpGrid function of the noise generator with that scale value. And that's it. That is how to implement a very basic texture using gradient noise. Now, I talked about how we actually really want to use the noise, value noise or gradient noise, to perturb another function, and that can create the much more interesting patterns like we saw in the animations at the beginning. So I want to show a very simple example of a texture that I call marble, because it can be made to, I think, reasonably closely resemble marble, you know, give or take. And so I just want to show how I've gone about implementing something like that, which I hope will be of interest. So let's have a look at that now. Okay, so here we are. I've created a class called marble, marble textures, marble.hpp. We bring in, of course, hash include the gradient noise generator we've just talked about. This, of course, goes into the texture subnamespace of QBRT, create our class marble that inherits from texture base. So we have our standard texture things, and now we've got some new stuff. We've got set color map, set amplitude, and set scale as before, but this also has a function called set min max and set sign. Now I'm going to talk about what those do in a moment, okay? So, but you can probably guess from the names of the input set, the set min max accepts a minimum value and a maximum value, and that will define the minimum and maximum values of our final texture, and set sign sets the amplitude and frequency of our sign functions. Okay, pretty simple. We store the color map as before. We store a list of noise generator instances. Now this is important. We don't just have a single noise generator now. We want to have multiple noise generators. As I talked about in the introduction, this is the concept of layering multiple noise generators together to create multiple levels of detail. Okay, so what we do, rather than simply defining one or two, we just simply create a list of them, and then we can have as many as we like. It's just a simple way of working. Okay, so we store a list. It's an STD vector of type QBRT : noise : GRD noise generator. We call it m_noise generator list. We have the amplitudes. We actually store just 2 amplitudes because in this instance I'm only going to use 2 noise generators. Obviously you could store those as a vector as well, and the same for the scales. We set our scales to 4 and 40. So this is, as I talked about in the introduction, the idea that the different layers of noise generators define different levels of detail. Okay, we set our minimum and maximum values, minimum value to -1, maximum value to 1, and we define the underlying sine wave parameters, an amplitude of 0.25 and a frequency of 4 initially. Okay, that's it for the header file. Let's have a look at marble.cpp. Okay, marble.cpp, let's have a look. We bring in our header file that we've just talked about. Now in our constructor, we now need to initialize our noise generators, and we have a list. So we use m_noise generator list. We call the pushback function, and we pass to it a instance of the noise generator and a second one. Okay, so that will create a list that will add, we'll add 2 noise generators to the m_noise generator list variable. We then configure those, so we set up the grid for the first one to be 4 and the grid for the second one to be 40, and we modify our minimum and maximum values. In this case it will be -3 and 3. Our destructor, we don't need any code for that. In our getColor method, we have the standard code that we have for everything. If we don't have a color map, we output purple. Now this is where it's different. Okay, so here the base function, right? Instead of simply interrogating the noise generators, what we first of all do is we create a sine function. So we start with our sine amplitude variable, we multiply that by our sine, and then this is a sine of m sine frequency multiplied by pi, multiplied by nu u plus nu v divided by 2. Okay, so that creates the basic sine of a frequency given by sine frequency and amplitude given by sine amplitude. Now, the interesting bit is we're now perturbing the phase of that by adding to it the value from our first noise generator, so noise generator list at 0, get value nu u nu v multiplied by m_amplitude 1 plus the value from our second noise generator, also at u and v, and multiplied by m amplitude 2. And what that does is we're now using the values from the noise generator to perturb the sine function rather than plotting the values themselves. Okay. And then we're going to use std clamp with map position, that's the variable we've just calculated, minus the min value divided by the difference between the minimum and maximum values, and we clamp that between 0 and 1, and then we simply pass that to the getColor method of the color map instance that we've created, and that gives us our local color. Okay, so hopefully that will make sense. It might seem a little bit complicated, but I think if you look back at the slides from the beginning, the animations where I showed how this works, and compare the maths I showed there to this code, I really hope that will make sense. Okay, I may not have done a good job of explaining it, but it's perhaps not as complicated as it seems. Okay. Right, and that's basically it. We then have a function to set the color map. That's exactly as before. It just stores the color map and sets the flag. Set amplitude accepts 2 inputs, amplitude 1 and amplitude 2, and simply stores them. Set scale accepts 2 inputs, scale 1 and scales 2, and stores them, and calls the setup grid method of each of our noise generators. I mean, again, if you wanted to have more than 2 noise generators for more levels of detail, you could simply replace all of these with arrays, and it's pretty straightforward. We have our function to set the minimum and maximum values. It simply stores those. That's easy. And our function to set the sine wave parameters, which simply, again, stores those as before. That is a very basic texture that implements a marble-like pattern. So before we can actually see what that does, let's just have a quick look at how we can modify the scene class to actually show off our new textures. So I'm just looking at the CPP file for the scene class. I mean, we haven't changed a lot. Obviously, we bring in basic noise.hpp and marble.hpp that we've just talked about. And we create some color maps, exactly as we've done before. So we create noise map, cloud map, marble map, candy map, and wood map. So all I've done for those is define stops at a number of different values. This is a nice way of making the marble-like texture. So I've defined 2, 3, 4, 5 stops for that, starting at white to yellow and so on, orange, whatever. Candy map is a very simple one, and wood map is also quite simple, so I've just made some nice brown colours there for something that should closely resemble wood, or ish. We create the texture, so floor texture, that's just a basic checkerboard we've done before. The value noise texture that we used in episode 15, the previous episode, exactly as it was there. Maybe with a different scale now, 16 and an amplitude of 2, but otherwise the same. Marble texture, we create this way. We simply set that up with a color map, marble map, amplitude of 4 and 2. So the amplitude of the first noise generator is 4, second noise generator is 2. The scale of the first one is 6, scale of the second one is 40. Okay, so that's really important. So the second one is adding fine detail to the coarse detail created by the first one. And we set our sine amplitudes to 1 and 4, and our minimum maximum values to -1 and 1 respectively. Cloud is made from the basic noise texture. It's really very simple. We set the cloud map to the color map, set the amplitude to 12 and the scale to 10. A spiral pattern, which we create using the candy map that I talked about just now. And so this is actually a different implementation of marble. It's just how you can use the marble texture to create different patterns. So what we do now is we simply set both amplitudes to 0. So what that means is we're not going to get any input from the noise. We are simply going to get the sine functions, which we set the scales to 1 and 10, the sine amplitudes to 1 and 8. Okay. Just that, and I've defined a transform there for that, but that is actually set to the default values. Of course, with all of these textures, we can translate them in X and Y, we can rotate them, or in U and V, sorry, we can translate them in U and V, we can rotate about the vector normal to the texture, of course, and we can also scale in U and V. Okay, but that's not translating, not scaling, and it's not rotating, sorry, and scaling to 1, so it doesn't actually do anything. And wood, very much the same thing, also from marble, but we've just tweaked the amplitudes and the scales and the sine values to give what we want. Okay, and then as before, we simply create materials for each of those. We have the value noise material, the marble material, the cloud material, the candy material, and the wood material. Okay, and then we've just set up the objects. Okay, so in this case, we've just got 5 spheres that I've set up. We've talked about how this all works before, and the floor, and so on. So that is it for the scene class. So let's go back to the terminal. Let's compile this, let's run it, and let's see what we get. Okay, so as always, I'm using gmake with the make file. It's included in the repository if you get it from GitHub. So simply going to let that run through and compile everything. I did test this before, so there should be no errors. Famous last words. Hopefully not. There we go, good. So let's just run that /QBRay and let's have a look what we get. So as always, that runs through and we'll render every line of our 720p image. It's not the fastest ray tracer in the world, I'll admit. Okay, and there we go. So that's what we create. So in this case, let's just talk through what we have. So this sphere here, the yellow and blue one, this is the basic value noise, simply plotting the value noise on its own without any other functions. The cloud one was the basic implementation, is simply basic gradient noise. We're not using it to perturb anything. And the other 3 are created using variants of the marble texture. So this one is obviously designed to look like marble. This one looks a bit like wood, okay, with a pinch of salt, I admit that. And this is the spiral texture where we set the amplitude of both of the noise functions to 0 to simply give a sine function like that. Okay, so there we go. that's really everything I wanted to talk about today. Another quite short, quick video. Compared to some of my earlier ones, but it demonstrates, I think, how we can use procedural noise to really start to create some very interesting and much more sort of natural looking patterns and textures, which obviously in the world of computer modeling and ray tracing and graphics and things, it's obviously really quite a useful thing to do. So the same caveat applies to this one as I talked about in the previous episode, that I haven't talked about hashing functions or using pseudo-random sequences to define the values of the vectors at the corners for the gradient noise. So the reason I haven't done that is because simply I don't need to. For me, I'm never going to be creating textures that are so big that I really need to worry about the overheads of storing a random vector at every corner. So it's just not really a big deal for me. If you know, probably if you be careful if you're looking at some kind of coursework assignment or something like that, because they may require you to implement a hashing function. And the reason this is sometimes done with procedural textures is really just to make sure that the size of the texture isn't limited. So by storing the value at everything, you are effectively limiting the size. If you use a pseudo-random sequence or a hashing function to obtain the vectors at every corner, then of course you can have a texture that isn't limited in size. Okay, so, and there probably performance improvements and things as well. Again, that is not something that I personally need to worry about for the application that I want. Anyway, there we go. That, as I say, is everything that I wanted to talk about today. So I think that's all been quite interesting, and I think, as far as I'm aware at the moment, I'm thinking that's probably the conclusion of my mini-series on procedural noise and procedural textures for now. One obvious extension to the value noise and gradient noise that I've talked about is to extend them into 3D. It's quite obvious, I think, if you look at the maths I've described and how that could be done. And that, of course, brings with it various advantages, particularly in that you don't need to worry about UV mapping. If you look at the sphere example that I showed before, one problem with UV mapping is you can see that it pinches the texture up at the top and bottom of the spheres. If you define the texture in 3D, then the sphere is effectively cut out of a bigger block of texture. So then you eliminate those problems, which can be good. But again, for what I want to do, I don't need to worry about that. So I haven't really talked about that. Okay. Right, well, okay, that now this time really is everything that I wanted to talk about in this episode. So it just leaves me to say thank you very much for watching. I really hope you've enjoyed it. I had a great deal of pleasure making it, so I hope it's been interesting and useful for you. And yeah, if you like this video, please do remember to hit that like button. And if you haven't subscribed to my channel already, please consider doing so. I do try to make content as regularly as possible, so if you subscribe, you don't need to worry about missing anything. Thank you very much. Anyway, that just leaves me to say that I really look forward to seeing you in the next video. Thank you very much for watching. Bye.